following up about this Axe news. So if there are events, for a long time we've been thinking of having some special issues in some journals. We did have one with developers. We plan to do something that is more scientific in the sense that it's going to be perhaps more applied to scientific applications that are using the Axe. And we are going to send it to all the people that have been coming to the Axe workshop. So the presentations, as you know, they are going to be online. You may want to check because, for instance, Cyrus is going to send us his. Are going to be available perhaps in a week because we needed to get some. He needed to get some clearance, from the lab before we can put it there.
Also, the pictures we are. Catherine just took some more pictures. We'll be creating an album and put it there in the website as well.
So collaborations. So obviously, this venue has been very good in spawning some collaborations. We talk about postdoctoral positions that somehow had happened, or even permanent positions. So let us know, when we send those Axe news, if you see something that is of interest, or you have questions about, jobs, we can put you in contact with people here at the lab. Or if any of the speakers that you would like to contact, also contact them directly. All right, so an important collaboration will be this, your training accounts are going to be open, I think, until October 2nd. But, hopefully, and that's for you to, with allocation on Carver. The only thing that is going to change is that the privilege queues are going to go back to normal. But you still should be able to run jobs, on Carver. Then after that, I'm recommending that all of you go to the NERSC website and look at these startup accounts. Startup accounts, it's really free. It's just a local review for a year, and you get to use the resources. Then after a year, then they are going to ask you to submit a competing allocation. And that competing allocation, as Harvey mentioned during the first day, they are actually coming from DOE. DOE makes the final decision in Washington. They decide who gets allocation and how many hours. So I think it's a very good opportunity, at least if you do it within the next month, you will really get your allocation good for a year, because the next review process is not going to be until next September. So, okay. So these are two links where you can find more information about Lawrence Berkeley and our division. Okay, so one of the questions that I got asked, and I found that it was very interesting, and it's great, is, how do we, you got all these tools, and we've been telling you, well, just go to the website, download it, install it. So I'm going to give you sort of like my bit of, or my small recipe of what I think that is the most effective way to install some of these tools and put them in your system. So we talk about all these general purpose tools, and if you remember that graph, so one thing that is important is that, I should put this on. Is that we need to, so all of them have sort of this common platform, and because the parallelism is all expressed still in that programming model that depends on MPI, most of them. I don't know about visit, do you? So it's an MPI. So you do have to have your MPI. So what I would say is that, make first the choice of compilers that you have. Remember that for some compilers, especially some of the GNU compilers, you may have some implications on the quality of the computations that you are doing. So make sure that you have good quality at that level. Then look for your MPI. If some systems, you may have ACML, MKL, or any mathematical library. If you have a mathematical library, it's highly likely that they will have BLAS and LAPACK installed. If not, you can go to the netlib, and download your BLAS and LAPACK. The next step is that if you run Atlas, it will produce optimized versions of of these libraries and of the blast of LA-Pack, and then you can start sort of like the base, what I call the basic set, tools. You need to have MPI, a good compiler, your libraries, and you can install any of those tools. Then, if you need to install SuperLU, you need to install one tool more, and it's Metis. If you want to install Scalable, you need a couple more tools to install. And it's because Scalable, so this is sort of like LA-Pack depends on BLAS, and you'll see here. And then for Scalable, you also need to have the BLACs installed and the PBLAS. So you start with the PBLAS, and then BLACs, and then you install the PBLAS, and then you're ready to install the Scalable. Then the Trilinos library. It's self-explanatory. Once you have this good versions of these libraries, then you can start building, the whatever is in Trilinos. Or you can, in some cases, if you have the libraries installed in the right directories, Trilinos can find those places for you if it's in the standard directory. But if you have your own installations and you put it in separate, then you have to use some command lines. If you want to find out what those command lines are, the best thing is to type help, with the CMake or the configure scripts. It's going to give you the whole list of all the keywords and how those keywords are used. So next is Petsy. And okay, so here is where I sort of claim a little bit more ownership on this suggestion. And it's that, yes, I know that you can go and ask Petsy and said, Petsy, I need Hypre, I need all these other packages, I need SuperLU, and do an installation. What happens is that in most cases, their versions, they keep versions of those packages that may not reflect the latest versions of those packages. So that's why I said, install your SuperLU first, install your Hypre, you have the latest, you can put whatever you want, and then you tell Petsy where those packages are, and then you can link with those packages, okay? So you do it separately. So the interesting thing here is that, for instance, Petsy can use some of the functionality that is available in Trilinos. So if you have your Trilinos installed, you can tell Petsy what that library is. Then you install your Petsy. And let's say that you want to do the opposite. You want to do also Trilinos to know where Petsy sits. So once you did that, you can go back to your Trilinos and reconfigure and add another configuration, which is going to provide you with that extra interoperability. Okay, but once you have a good Petsy installation, you have all the packages that you want. So this is a sort of difference. Petsy, in this case, is going to call those packages, or Petsy interoperate with those packages. So those are independent packages. You have them installed. You linked it, and then so the next step is, we get our SLEPC and Tau, which build in a matter of minutes after you have a good installation of Petsy. For Tau, there are a few alternatives. Depends what you want to profile. So if you just have this basic elements, you have your compilers, your MPI, your OpenMP, you can install a very basic version of Tau. But that's the only things that you're going to be able to profile. If you want things like automatic profiling, you want Tau to do a lot of things, then you need this library, PDT, which comes in the Tau distribution. You install PDT, and then you go up and install Tau. If you want performance hardware counters, like PAPI, then you have to have the library. In most cases, they are installed. You just have to find out where these libraries are and tell Tau where they are. And KUPTI, which is for your GPU architectures. So, and that's all that I have to say. Are there any questions? Yes?
So I just wanted to say, and if anyone was listening online, this is Joe Bernstein from our international.
Should I make a comment about the mountain line?
Yes. Yeah, I think so. How many people are staying at the lab? At the guest house. Okay.
There has been a sighting of a mountain lion
female on the line with 2 cubs
With 2 cubs by the entrance of the laboratory?
this morning.
Yes.
So if you're on the shuttle bus, don't stop at the gate and decide to walk. Or if you decide to walk, just don't go like when it's dark. Use a cab.
Yes, in particular this one, because it's a female with 2 cubs, you don't want to get any close to her. She will try to.
So the best is if you take the bus. Actually, so it's really at the entrance of the lab, so it's by the guards. So what I suggest if you're planning to go back to the hotel and walk, go when there is a lot of sunlight and there's still traffic going. Don't do it late at night. And if you need to do that, do it with a taxi or the guest house pays for the taxis anyway.
Yeah, she's looking for food, which is in this case is deer. But in any case.
Okay, so with that, I'm going to close this if there are no questions. And we just welcome Cyrus from Lawrence Livermore, and Harry, who is also from Lawrence Berkeley. And they're going to talk about the visit, which really, is the reward for staying here, because in most cases we need to put all those pretty pictures and do all this, and do it efficiently, and they do a great job with the Visit Library and have won many awards. So,
okay. Thank you very much. So, question: am I on here? Is my mic on? I think I just turned it on. Yeah.
No, it's good.
That's good. Okay.
Yes. Is not Apple employees roaming around.
Right. The same.
So yeah, Mountain. That's kind of exciting. If you see a giant cat, don't stand and take pictures. Probably leave. That's a little scary. So thank you very much. So as Tony said, I'm Cyrus Harrison. I'm from Lawrence Livermore National Laboratory, and Hari Krishnan from Lawrence Berkeley National Laboratory. We're going to give you a short introduction and a little bit of a hands-on tutorial about Visit, which is a parallel visualization and analysis tool. So I'm going to wander over here. I hope the video will keep up with me. So here's the original schedule. We're shifted by a few minutes. But basically the plan is I'm going to tell you a little bit about the Visit project and just give you some background. I'm going to do some walkthrough of the code just to get you familiar with it. So pull it up, do some clicking around, and show you some of the features. And then after that, we're going to spend a couple minutes helping you get Visit installed, so on your laptop. So, hopefully we can get most of you installed. You know how these things go. So, hopefully we can get most of you installed pretty easily, and then you can follow along a little bit later on. Later on, after the break, we're going to, and we might shift the break around. If you guys stop me, if you since we've shifted things, stop me if you want to use the break earlier or whatever. We're going to do a client-server demo with Visit, so we'll try to show you how to connect Visit to Carver, which is, I guess, the machine that you guys have been using at NERSC for your accounts. So we'll show you what we mean by that, where you can run locally the Visit client and have the heavy lifting be done on that machine. And then we're going to do a little tip on scripting Visit and kind of wrap it up with where you can get more information on how to use the tool. So that's what we're planning on doing. So I'm gonna go through the project introduction and do some of the basics. I'm gonna hand it over to Hari. Then we're both gonna help you get stuff installed. So introduction. So what is Visit? Well, it's a large-scale, massively parallel code for doing visualization and analysis of mesh-based data. So if you have your simulation meshes, your Eulerian codes, your Lagrangian codes, even particle meshes, Visit's the tool that you can use to get pictures out, to do analysis, etc. So it's more than just a GUI and an application. It's an infrastructure that you can use also to script and to write custom post-processing for your jobs. So you can do a lot with the tool. It's both a tool that's standalone, productized, but it's also a platform that you can build your own analysis on. Visit's open source, completely open source. It's released under a BSD-style license. And the source code's out there. If you're interested in knowing where that is and all that stuff, I can answer those questions. But it's available. And of course, if you're really excited and you want to develop Visit, we welcome that as well. So, if you get really excited, send my emails in the slides. But, talk to me, send me an email. Maybe there's something we can't do that maybe you could help us do. And I'm going to not talk about this pretty picture, but we're going to talk about some other pretty pictures in a minute. So what can you do with Visit? So Visit is kind of poorly named. So you think Visit, well, there's a couple reasons, right? We do more than just pretty pictures. Pretty pictures are very important for a visualization tool, obviously. But we also, as I said, we're part of this larger tool chain. You can do a lot of interesting analysis and post-processing with it. The other reason why Visit's kind of poorly named is that if you went, and some of you maybe have already done this, if you go on Google and you type in Visit, you're not going to get our product. You're going to, last time I talked to somebody, it was right before the Olympics was starting, and I think, it was Visit London or whatever. Now, did you get Visit come up?
We embarrassingly got it #1.
So that means Google knows too much about you. That happens to me too. So that's good. Yeah. So we say Visit's kind of poorly named because of those things, and it is used for more than just making movies. So what do? Well, any visualization tool, you got to be able to get into your data and explore it. So we have the types of tools that you need for slicing and dicing your meshes, resampling things, creating all kinds of different plots. So as a user of a scientific simulation code, you don't want to just watch a movie of your data. You want to say, oh, that little spot there is interesting to me. How can I get in there? How can I get more information on it? So we have a wide suite of tools that allow us to do data exploration. And that's really how we see it used most of the time by end users. They're not always creating PowerPoint presentations with pretty movies. They're doing daily work, and they're interacting with their simulation codes. And so data exploration is a big use case for us. Another use case for us, and it goes along the lines of not having just pretty pictures, is quantitative analysis. So with data exploration, you get a qualitative feel of things. So you see how things look, but you really like to know, well, what's the value of my hotspot that I'm looking at? So we have sets of queries and analysis tools that allow you to probe your data and say, okay, where's the maximum value? Things you would expect of that. So data reduction things. Another important use case is visual debugging. So if you're running a simulation code, say it's a Lagrangian code and things start to bow tie or twist, things are going to go wrong, your code's eventually going to crash. You don't always want to pull up a debugger, especially on 2,000, 10,000 processors and say, what's going on with my C code here? What you want to do is you want to look at your mesh and you want to have some tools that allow you to say, here's where things are going wrong. So by looking at your problem in Visit and using that to steer, go back and fix your simulation, you can get a better feel, in the problem space what's going wrong as opposed to maybe in the code, which you can be orphaned pretty easily there. Another use case is comparative analysis. So if you have two different meshes, you'd like to say, what's do differences between them is one example. Of course, you can always do that with the squint and look and say, oh yes, these look the same, but you want quantitative. So Visit has a way of mapping meshes, onto each other and doing doing that in parallel. So you could take two meshes and map one field onto another and do some subtractions and stuff. So there's some cool functionality there. And finally, presentation graphics. Well, we aren't all pretty pictures, but we do have pretty picture, capability. So it's important. Communicating results is important. Being able to produce movies, being able to make nice, nice presentations for grants, et cetera, all that's very important. So we have to do that as a visualization tool, and we do.
So a picture speaks more than 1,000 words, but when it's a pretty one, it's
yes, exactly.
only remember.
Exactly. So, presentation, presenting your results, the picture goes a long way. So it's very important. So what kind of things can Visit do? Well, it can do a lot of things. This is just kind of a random collection of some of the plots we can do. One of the really interesting things we have is it's a really advanced parallel streamline capability. So there's lots of different ways to integrate fields, and basically if you have a velocity field and you want to drop points in it and see where they flow around, we have a parallel capability that's really on the top end of all the Viz research that's been going on the last few years. So the streamline capability is really interesting in Visit. We have ways of viewing vector and tensor fields, so glyphing, pseudo color plot, which is where you have a field and you want to map it to some color map. That's kind of your really standard bread and butter. We have scalable volume rendering, so we can cast rays through your problem, and you can apply a transfer function, so you aren't just looking at the outside surface, but you can get an understanding for the features inside of it. We have some molecular visualization, although I'd say we have a basic capability here. We'd like to do better, but we have some of that. And we also have a little bit of information visualization, such as parallel coordinates. And what parallel coordinates allows you to do is take a whole bunch of different variables on your mesh and plot them and see the feature space. So in this example, these could be density, pressure, et cetera. And let's see if I know how to do this guy here. And you can get a handle for correlations between different variables. So that's just a example of some of this stuff. So when we do tutorials such as today, we don't have much time to do really interesting things. We're usually playing with toy data sets, which is one of the criticisms I've already heard you guys had. So you're going to get to see us play with some toy data sets. But what kind of real stuff are we doing with Visit? Well, we're doing a lot of interesting things. This is an example of something that I'm working on. So basically, we have these big DNS simulations, which are very high fidelity of fluid mixing. And they're very expensive to run. But in the fluid, in hydrodynamics world, you also have different models like RANS or LES, et cetera, these different models that model the turbulence. And what we're doing with Visit is we're using Visit to post-process our DNS simulations and do specific averaging in it. So we can compare our models from our RANs to, say, the DNS simulation and try to validate them. So we're actually using the parallel framework of Visit to do these means and fluctuations and define these closures and all this stuff. And so that's an example of using Visit, not just to make pretty pictures, but to create a post-production, basically, tool that, and since most codes, Visit can read most codes, then it's one tool that many codes can use. And this is work I'm doing with Oleg Schilling at Lawrence Livermore. But sometimes we see that the best thing to do is invest in Visit, because if we can get a code into Visit, that's a little less effort than writing this code in 5 different, writing this post-processing code in 5 different things. So that's just an example. Another interesting thing about Visit is that it scales very well. So about 3 years ago now, the Visit team put together a paper on testing scalability of Visit. And around that time, I also did a stunt calculation on a Livermore machine. And what the important thing here is that, obviously these numbers are huge, but 20 trillion or 20K cube and 8 trillion zone mesh, that's an insanely big mesh. And this was done a few years ago. Basically what we wanted to do is we wanted to make sure that the tool wasn't going to fall apart, and we wanted to look at the I/O and all that stuff. But everything works and everything holds together. So Visit at scale also works, but it's not just pulled out for hero runs. It's not just pulled out for the biggest of the big things. It's an end user tool that's used daily by domain scientists. So it's something that you could use. You don't just run to it when you have the grant to work on the world's fastest supercomputer. It's a useful tool for everybody. Yes?
We are using Visit interactive radio, right? So why I care about scale to 16,000 processors? I don't have that large machine.
So if you don't, that's what I'm telling you. So for instance, if you have this big of a data set, and so these guys here are rendered, basically the volume rendering and the thing. If you have this big of a data set, it's still going to work if you have a big machine and a big data set. But if you want to use an interactive reader on a laptop, it works as well. So why do you care? You care only if your data is that big, and you care only if you have enough money to have the computer to run it on, but it still works. So so good question though. Good question. So I'm gonna speed up a little bit here, but just the takeaway from this slide is that Visit it's been around for about 10 years in production. It's a robust tool. We have a large team working on it. We do regular releases. We have documentation. We have all the things that you would expect from a software product. So we're there. We also do a lot of outreach where it comes to tutorials like this, or we have mailing lists that you can contact us on. So if you're interested in using the tool, figure out how to talk to me or talk to us, and we can help you out if you're having some problems. Again, along the lines of Visit being kind of this robust tool, this is a little bit of the history of Visit and where it started. So it started at Lawrence Livermore National Lab around the year 2000, and after a couple years, and it was part of the Advanced Scientific Computing program there. After a couple years of prototyping, et cetera, the project was the users at Livermore were transitioned to use the project. And then after a few more years, basically Visit, I wasn't on the team at the time, but Visit, they saw that they wanted to become more of a player in the broader visualization community. So they decided to go to open source the tool, go through that, have a completely open repo, and got involved in some of the DOE SIDAC programs, et cetera. And that was, basically what opened up Visit to the rest of the world. And we're a vibrant team now. We have people working on it at over 5 different institutions, 3 national labs, and 2 primary universities. There's also random people who help us speckle around the world. And it's, it's been around for a while, and it's had really good success because we have this team behind it. So I talked about, I'm telling you a lot about Visit, so what kind of data do we deal with? Well, we deal with the mesh types you would expect, curvilinear, unstructured mesh, et cetera. We deal with scalar, vector, tensor fields, and we have a lot of different ways to get your data into Visit. So there's over 110 different file formats, and there's a plugin architecture that allows you to write your own. If you have, if I had Cyrus's custom format, I could go and write my own reader for it pretty easily. So we have a very good data model that allows you to get a lot of different types of data.
Yeah, good question.
Yes.
So how much work do you need to do if you have some exotic mesh that is not supported?
So define exotic, I guess.
Maybe like a shell file that is 3D, but it's more like a 2D kind of.
I think you wouldn't have too much. So the only weakness of Visit now is higher order element support. So we have some higher order element support for finite elements, but we don't have a very good foundational model for that. But if you have, we deal with basically a lot of regular finite element types. So if you have wedges and tets and triangles or shells, and we deal with RZ meshes, and we deal, revolved meshes and these things. So basically, to answer your question, you'd really be just basically getting your format into the data model that Visit already has. And we could probably talk offline a little bit. I'd probably be able to help you out a little bit more with that. But it's probably not too much work, and it might already be, there's some way to read your format. So.
How
Yes.
high order is high order?
How high order? So zonal fields in Visit are piecewise constant. Nodal fields are linear, interpreted linearly. So anything other than that is higher order.
Okay, but I mean, do you support P2 or P3?
So I don't know. So that's a good question. We don't go very far. We have specific cases. And I'm not sure which ones they are. I'm not used to it as much because I'm used to more working with Eulerian codes and Lagrange. I'm not used to working with finite element code, so it's not but we have some support, so we can figure it out.
What about DG?
What's that?
What about discontinuous fields?
Discontinuous fields? Yeah, I don't think we do a good job there. Yeah, but we're interested in talking about what improvements to our data model we can make. Let's see, how am I doing on time here? Okay, so this is kind of a snapshot of the software architecture of Visit. You may or may not find this interesting, but we're a parallel scalable tool. How do we do that? We have a client-server architecture. So all these guys over here, which you probably can't see the laser that well, they basically can live locally on your laptop. And the main guy who's in charge of everything is the Visit viewer. It controls all the state of the system. And it also shows you, it basically renders everything. That's the Visit viewer. And then we have all kinds of clients that can connect to it. So we have a Python scripting client. We have a GUI, which you'll see me drive through. And on the back end, we have a parallel engine that does all the heavy lifting. Now, this says MPI here and stuff, but on your laptop, it'll still fire up without MPI. It'll run serially. But we have the Visit engine, which reads in all the data, does all the data transformations. And that's how we're able to scale to large core counts. We have the state abstracted over here, and we farm that off to the heavy lifting. One really good thing about Visit is, well, if you have these big data sets like you saw, those huge ones, you're not going to be able to bring those back to your graphics card on your laptop, no matter how many millions or thousands of dollars you spend on that laptop. It's not going to work on the biggest data sets. So you have to have a way of rendering in parallel when it counts. And if your data size gets big enough, Visit will automatically start rendering on the engine, doing things in parallel there. and it'll just send pictures back to your laptop. So you're just getting pictures back instead of all this geometry and crashing your operating system. So scalable rendering is a good feature of the tool. I touched on this a little bit earlier, but we like to see Visit more not as just a tool, but as a platform. So we have Python scripting is probably the most powerful way to do a lot of custom analysis. We have ways of writing custom interfaces for Visit. If you hate the interface, there's ways you can write new interface, and you can steal parts of Visit's interface, use them in your own tool. We have that in Python, Java, and C++. And we have some other interesting Python interfaces that allow you to do lower level data analysis. We won't talk about that here, but all these things are a foundation for creating a platform for doing visualization analysis post-processing. Last thing I'll mention is libsim, which is a library for in situ processing. So if you wanted to link Visit into your code, you can hand us your mesh data structures inside of your code and avoid copying them or writing them out to a file, and fire up basically within your simulation Visit's engine, and then connect to the GUI and do things. So that's another interesting feature that we have. I think I want to skip forward here a little bit. I'll just say that, like I mentioned before, that Visit's starting about 2006, Visit started to become open to the broader visualization research community, and we're involved with a lot of different research. Parallel streamlines were one of those efforts. VASIT was the primary thing, a DOE SIDAC program where a lot of those efforts were centered. And going forward, we're part of SDAV, which is another DOE program similar, and we're collaborating with a lot of other folks to do some interesting things. So I'm going to, oh wow, so we're not going to be able to see that on the screen, are we? I'm going to go ahead and start driving. Yeah. It's the HTTP. So you'll see it when I, let's open up here. Exit the show. Oh, that's interesting. My computer's going to die on me here. All right. So we're going to go through some of the tutorial stuff. This stuff is outlined. Oh, I can make that bigger. This stuff is outlined up here, and so when I do get you the slides next week, they'll have the links to this. But all these are off of our users wiki, which is visitusers.org. And I'm just going to drive you through the tool for a little while and give you an introduction to it, and then I'm going to hand it over to Hari. He's going to show you some other features. So again, we're going to go ahead and show you, help you get installed and everything later. But I want to show you a little bit about what the tool can do before you get your hands on it. So this is what happens when you open the tool up here. So this right here is our GUI, and this is one of our viewer windows. So that's where you'll see plots. And to get started, you always start by, oops, I don't want to do that yet. I don't want to ruin the surprise for later. Well, to get started here, you're going to end up opening a file, some sort of file format. I'm going to have an example file here. And basically, your file browser allows you to go in and select different files. You can also, Visit tries to be smart, and then it tries to figure out what your file format is, so it goes through a whole bunch of checks. But if you're smarter than Visit, which you probably are, you can tell it explicitly. I know I want, for instance, an Enzo file or a Silo file or something like that, and you can set extra options. So if Visit's failing and saying, I don't know what your HDF5 file is, you would go here and set more options in order to deal with things. I'm going to just let Visit do it, because I know it's smart enough here. And now I've opened a file. One of the criticisms of people have of Visit is, I started Visit and I opened a file up and nothing happened. And I say, well, yes, you're doing everything correctly. So one of the things of being a scalable parallel tool is we don't always want to do things when they could be expensive operations. So we want to wait till you set something up until you tell us you want to draw it in order to do something. So Visit has 5 primary different things that you deal with. We've already went through one of them, which is a database. That's how we get data in. The second is called a plot, and that's how you view data. So over here, we have a plot list. And this plot list tells us, the different options that we have of the different plots that we can create. And for instance here, I'm going to create a pseudo-color plot from our noise.silo file. And I am going to select a scalar field, which I know exists, that's called Hardy Global. Now again, someone say, well, I just added a plot, but I don't see anything. Well, yeah, we got to tell Visit to draw. But up here, this is going to have basically a list of all my plots that I have set up. And I'm going to go ahead and draw it. And then you see over here, this is a toy data set. It's a rectilinear grid with a field on it. And we can see that over there. So I'm going to take a sip of water real quick here. Let you stare. You can stare at that for a second while I do this. So we have our plot here, and if we want to modify the attributes of the plot, we can double click on the plot name. So in order to get there first, actually there's this little arrow that expands out your plots so you can keep them compactly. But if you want to change some of the attributes of how things are rendered, this is where you would do it. So you double click on the pseudo-color plot, and I can then go ahead and I can change the way my color map's applied to a log scale. I can pin different minimum and maximum. So you basically get a different view of your data set by doing that. And I can set the opacity as well. So I can make things sort of transparent. So this is basically how you interact with the different plots. And I'm going to go ahead and kill this guy, and I just want to show you how these basically you can have multiple plots in the same window, and everything works. So we have this. Okay, this shows you your scalar field, but if we'd also like to look at our computational mesh, well, we can make a mesh plot of, in this case, the variable name is mesh. That happens to be the mesh name in the file. And if I draw that, now you can see the grid of the actual mesh of the code. So this tells you basically where your mesh grid lines are. So this is a rectilinear grid, so you're looking at a whole bunch of cubes here.
So is that the mess with the values, is that the visit handling of the mesh?
Yeah, it is. But so for instance, if you have a decomposition of your mesh that your simulation uses, then you would be able to see that in Visit. Visit would be able to create plots of that. So it's how you provide the Visit.
Sometimes the tool interpret the quadratic mesh to be a four linear mesh.
Yeah.
So do you do it that way, or you provide it?
So we do it whatever way you give it to us. We won't. So we have different operators, which I'll go over in a second, that allow us to slice and dice things. But we don't necessarily do automatic mapping for you. Yeah.
So this goes back to the way databases are generated. So when you read it in, we actually query this database to figure out what type of representation you're going to give it, and that's what it uses to render. So if you do decide to break it up into whatever you want, you will see that. Unless you do an operation like resample or something.
Yeah, then you can change the mesh. So you can hide and show individual plots too with this hide and show here. So if I wanted to only see the mesh and not the pseudo color, that's this guy here. And let's see here. I'm going to move along. And so I said we've already covered two basic things: the database, how to get your data in; plot, how you view your data. And the second we're going to go over is an operator. So I'm going to start with my my mesh here, and what I'd like to do is I'd like to take an ISO volume, or a set of, not ISO volume, let me not start there, but a set of ISO contours. So I can go into operators, which has a similar menu that allows me to select things, and if I go under slicing, I'll find this ISO surface operator, and you might be looking for contour. There's also a contour plot, but let me get there. ISO surface operator, and it's gonna do this ISO surface and calculate it and create a new mesh. So it'll modify the mesh, and now I have a bunch of surface meshes. And the way all those ISO surfacing operations are controlled is, again, we can go in here and we can double click, and we can say, well, I want 10 levels. Okay, well, in this case, it'll evenly space them automatically through your range, or if I want 5 levels, etc. So operators, so making a plot, you're going to see whatever happens. The pseudo-color plot is going to tell you whatever happens at the end of this pipeline. So if you do slicing there, or resampling, yes?
you have a documentation of all the equations and interpolation scheme are you using?
So no, we don't. But we have papers on it. We have various papers and stuff. I don't think we have a one place where you could go and say, how are you doing this? We have. So one of the things that Visit does, I don't want to get too far, but it has material interface reconstruction schemes too for volume fractions, and there's lots of different schemes there, Young's method, several other. This one's kind of like a marching cubes.
So you are using publicly cited theory equations and all? That's what I'm asking.
Yes, yeah.
And you are citing it so that we can go to that paper or?
I think,
Well, several
Ask
of them
us.
are very well known
yeah,
and have existed for so long that
yeah.
we don't really need to cite it. You can get references immediately.
Yeah.
And a lot of them use that.
Another question is, can we annotate with text?
Yes. So I'll just show you real quick that, and then we'll get back on track here. But there's different annotation objects, and I could add a new text object, and it's right now called that. Let's see. And I can.
I mean latex.
Oh, LaTeX. Not inside of Visit. You can't. No, you can't. Sorry. Sorry about that. I misheard you. Let's see here. So isosurface is one example of an operator. Another example is a slice operator. These are kind of some of the simpler ones. So a slice will just take basically a 2D slice through the mesh. You can also keep it as 3D if you really wanted to understand where it was coming from. So where it existed in the original volume. So this happened to be the slice plane that it automatically picked for me, but I can change the intercept. Jeez. So I could change the intercept, say to 5, and move it around, etc. So operators are a way for you to slice and dice your data. There's some more advanced things in there, resampling. There's connected components capability, a lot of different things. Hari's going to talk to you more about some of the quantitative things. This is just more of a loose look and feel here of what the operators can do for you.
Can you show the volume rendering?
Yeah, I'll show the volume rendering in a little bit here. Before I do that, I want to tell you just a little bit about some of the interaction modes of the viewer. So the viewer, which again is this window over here, by default you're in a navigation mode. So what you can't see, I'm sitting up here using the mouse, but I can. You see me rotating around, you see me zooming in. That's a navigation mode. We also have pick modes, which allow me to click on the mesh and pick and get my zonal values at a specific point on my mesh. So if I cared about what was here in this little hotspot, I can go into this pick mode up here, which actually, it's probably hard to see, but this little Z cross is a zone pick, N cross is a node pick. And those allow me to get a little bit, basically get information on a specific part of my mesh. We also have a lineout operator, and to do that, I'm going to make that easy. I'm going to put a slice back on here so you can see what I'm doing, which will allow me to take a line out from my mesh. So I clicked on the line out, which was up here. And say I'm interested in values along this black line here. I can drag this line, and I'll get another window that shows me the values. So that's one of the other interaction modes that we have. We also have an explicit zoom mode. So we have navigation. You saw me doing with my mouse wheel cheating and zooming in, but we also have explicit zoom mode where we can zoom in with a rubber band and. If I care about this region, I can look at that region, etc. So those are some of the interaction modes.
With that line mode, can I click on a contour? Just give me the values right there.
So you mean if you had like so you could do something similar like that, I think, with a spreadsheet plot, but I'm not sure. Spreadsheet plot's a little complicated, so I don't want to go into it now. But yeah, but you could certainly get the contour values out in many different ways. Yeah. So you also see me making mistakes here all the time, and I'm always clicking this guy, which is reset view. That's an important thing to know. Oops. So if you look up in this window, these are all view-related things. So I can save a view. So if I wanted to save a view snapshot, let me just do something, and I can. Is it this guy? No, that's. Which one? Oh, it's this guy, the little picture camera. So if I wanted to save this view and get it back later, I mess something up, I can recall my view. So that's very helpful. And there's an undo key for the view as well. So if you get too far in, but you know 3 steps back, you had something perfect, you can undo. And when abandon all ye hope, you reset your view and you're back to something sensible.
Can you draw the line again?
Yeah, sure. Sure. So say we're interested in looking at values along this line. And it didn't pop up the window because the window's already there, but it adds the line.
It's smooth, I think. Why here is something like the type of key like features?
Actually the reason why that's happening is because I've taken a slice through a smooth field. So there aren't perfect. It looks on the screen smooth, but I've taken a slice. I've changed the mesh. So the way it intersects with the mesh is making that happen.
And it could be confusing because maybe some data is really
Yes, exactly. So you have to, so by taking the slice of this, it's kind of a coarse mesh, and by taking the slice, it's done something to change the interpolation. So that's why there's little notches in there. Let's see how we're doing here. How are we doing on time here? When did we? So we were pushed back a little bit. We probably want to switch over to Hari, and let me just see real quick. Break. So I'll go ahead and hand it over to Hari real quick, and he's going to talk to you about two of the other basic building blocks that we have in Visit. So I talked to you about databases, plots, and operators, and he's going to talk to you about something called expressions and queries.
So I'm going to start with.
This thing's misbehaving, so let me get Visit up for you so you aren't.
Sure.
Yeah. And let me give you this too.
I think I'm loud enough.
You think you're loud enough?
Yeah.
Will the video pick him up?
The video?
Yeah.
I think. Yeah.
Do you need another one, or do you guys want to?
Oh no, I think one is.
Because you can use this one.
Yeah.
If
So I have some notes here, so I'm probably going to be following this myself. But in general, as Cyrus mentioned, I'm going to go over the other two. So you've seen, there are plots, there's operators, there are databases. There's 2 other modes of working within Visit itself. One is called queries to do your analysis work, and the other one is expressions, which also does something similar. So I'm going to go over a simple, again, a similar kind of a toy example. Yeah. And back to our little noise data set that you've seen before. And let's recreate a pseudo-color plot. Let's say a Hardy Global. Oh, this mouse is a little hard to navigate.
Sorry.
No. I think it's the trackpad, the mouse pad. It's way too smooth. So you guys have seen this before in a few other examples. I'm going to reuse this for consistency. And so there are many different types of options that you can control within Visit. As you can see, you can make movies, you can do keyframing. And the 2 explicit ones, one is expressions. I'll go over doing that a little bit later. And then further down below is this thing called query that allows you to take a data set and actually get values from it. So when you turn on the query options, as an advanced feature, Cyrus, we can always go over it later, but even expressions and queries can be done within our Python interface that exists within Visit. But for now, I'll just show you the default interface that we're using. So as an example, we have many different types of analysis routines, query routines that are available within Visit. So if I select something like variable related, and I want to get the min-max of the original data, it'll give you back, you query Visit, and Visit actually checks on it and gives you a minimum and a maximum, and what coordinates, and actually gives you extraneous information on that. And since you're getting the whole data set, the original and actual data will probably be the same since we have not modified it in any way. So the difference between the original data is the data that's coming from the file, and actual data is the current sequence of operations that you've done on it. So for example, if we go back to our window, I hope I don't lose this because this mode of operation is different.
You can look at the screen in front of you too.
Oh, that would be easier. So so let's say I made a slice out of it. So now it's a two-dimensional slice. And I want to query this information. And as you can see, it gives me back the same information as it did for the full data set. That's because we wanted, that's what the selection up here does, is it gives us back from information that is from the original data set. But if we want to apply whatever we've done to the slice and see what our actual data set is, you see now there's a new min and max. The values have changed, and you're querying the effects of all the operations that you're performing. So that, in a nutshell, is. Any questions? Oh. So you can do that with min max. You can do that with. So as Saras has already gone over, and I'll just gloss over it. You can do that. You can do picking from here as well. You can do lineouts on your variables.
So you can do lineouts programmatically. If you
Yeah.
drag it away.
So you can do -5, 5, 0, 5, 5, 0, and then say I want to query this, see if it works, and voila. So you can actually put in these values and directly get, so rather than drawing it on the screen, you can programmatically pull it up. So you can do other types of reductions and other types of operations. So you can get the variable sum, and it shows you what, I guess, it knows what units it's using. So it says, it's 8,880 units. Let's see, if we go back to the 3D volume case, and I want to query this, you get a different value, and it's for the whole data set. So there are many different types of operations you can perform on it, on the variable, on the mesh, on the curve, on the time. So you can get how many total zones there are, how many total nodes there are. You can get the 2D area, the 3D surface area for the original or actual data sets. So there's many different operations that are built into Visit that it will perform on your current selection or your current view that you're presenting, and be able to analyze and get values out of it. And you can do this on the Python CLI, you can do it on the GUI, or any client-related, any type of client that we have, you can get this information from. So you can technically use Visit chained with other applications, do analysis on it, and continue your workflow just as you were doing earlier. So, so to be quick, I guess I will do an.
We got time, so yeah.
So let's see. Well, we have gone over zone center. Here, the examples I have. Yeah. So going back to the query really quickly. So let's see if this is. You can do. So you can actually get the total surface area. And so I actually would like to try this one. So another example would be, should I try the connected components one? So let's see, let's add this back in. Already global. And I'm going to select the ISO volume one, which by the way, there's actually another way of getting them as well, they're under plots and attributes. So if you find selecting in the default way a little difficult, there are multiple ways to get these interfaces. So I'm going to change this to 4. Well, before I do that, why don't we do this programmatically or through iterations? So you see your plot again, selection. So, and as you can see, this only picks from 4 on up to maximum. And, well, the notes here say a bunch of blobs. OK, so now you can actually perform connected query components. Actually,
Oh, no, you don't want to do that. You want to do a query.
yeah. So. Which one is that on? Oh, there it is. And so I want to do, you have a bunch of selection mechanisms for these things.
You need to do,
just
do components, the last one.
So the last one is a component count, right?
Yeah.
Yeah, so you can get how many counts there are that it finds. In this case, you get 15 components that are available for these blobs that you've computed for instance from your ISO volume that is going from 4 greater than to maximum. So there are different types of queries that you can perform on these, and they can range from the very simple to the as complicated as you'd like, and you can chain a lot of them together.
Can you then access each of those components?
So
There's different ways to do that. So there's a way to actually use this and color everything by its component label ID.
Okay.
So from there, you can get information out of it, and you can apply further things. Or you can go into Python and get information about those things.
So, yeah, I'm actually doing something that he's very much intimately connected to. How long has then been?
So Connect Components have been Visit since 2007. And one of the interesting things about Visit's Connect Components is it does work in parallel. So if you're running in a situation where you have a huge mesh and you chopped it up and you have, say, some little crazy string of volume that wraps around many processors and all this stuff, the algorithm that's in there will handle that in parallel and make sure that you get a label that actually identifies things globally. It's one of the interesting analysis algorithms that we put in.
So moving on to expressions now. So any questions on queries? And so like I mentioned, a variant of these, an API actually exists in Python, and as you can say, you can drive pretty much all the queries that you're doing through the GUI in a Python function call as well. So a lot of these operations actually exist. So the expression is another powerful little feature. There's time-dependent components. There's you can actually cross multiple different meshes from different files together on top of each other. There's many different. Let's see if this is. So there are many different operations you can actually perform on expressions as well. And as I also pointed out earlier, that there is a Python version of this as well. So just for simplification, I'm just going to go with the original way of doing it. But there's a documentation on all the ways you would do this in Python as well in the visit user site. So, as you've seen Hardy Global a few times, there's also another variable in there called Shepherd Global. So this particular instance, I want to do some kind of computation on it. So I want to be able to say, I want to do the absolute value of one variable minus another. So you can actually type all that in, but you can also find out what type of scalars that are available within this mesh, within this data set. You can take a Hardy Global let's say, subtract that with the Shepherd global, and you can also name it diff. And you can actually generate different types of fields. You can make a scalar field, a vector field, tensor, symmetric mesh, area, and curve. We haven't actually gone through vectors too much. You've seen a picture of the streamlines. So you can generate any of these things on the fly as well. And there are examples, and we've used them in different ways. So if I apply this, one thing I'll show you is now if I come back to all my original plots and I start to do a pseudo-color plot, you will notice that it actually shows up here. So it knows that it's a scalar field, and a pseudo-color plot can actually generate one. So now this is the difference between a Shepherd global and a Hardy global. And we can, just to show the difference, I can create a new window. So there's also abilities to here, keep doing that. So you can actually compare all three of them. So this is our original, our newly diff data set, and both the Hardy global and Shepherd global. And you can do, question?
Yeah, I was going to follow up. What happened to that feature that you mentioned earlier when you can subtract so that you can see the difference between two results? Do you do the same thing with that expression again?
Yeah.
Yes.
Yeah, okay. So if your fields already live on the same mesh, then it's trivial. You do what Hari just showed you. So you can just write a little, it's basically a special language that allows you to subtract the two. If they live on different meshes, there's actually a wizard that has options that walks you through. It's a little thing that says, hey, are you doing it from a mesh in the same thing but a different time step? Are you doing it from a different file? And it walks you through defining an expression that will in fact do that and do things like, how do you want to map it? Do you want to map it based on position, or you know the connectivity is the same? So there's a lot of different ways to do it. But if they're on the same mesh, then you just use the expressions that, like Hari just said, because that allows you to take everything scalars on the same mesh and combine them and create derived quantities.
But most likely, you probably don't have the same mesh. Then you need to do your own interpolation to compare them.
Yes, yes, exactly. So yeah, so this is the wizard. We won't go through it here because it's a little more advanced feature. But this is the wizard here that Hari's showing you here that you set up. It says, are you doing it different time slices on the same mesh, between different files, etc. So that's there.
Yeah. And there's a mechanism for absolute and relative ways of computing. So you can do one ahead of you, one behind you, or an explicit static time data set.
Yeah.
Whatever you want to compute these expressions over. So, questions?
So I'm gonna pause right now. So we're at 2:35. So would you guys? So I'm going to go back and I'm going to show some of the other plots and stuff in a little bit. But would you guys like to take a break now and we can start getting visit installs going? Would that be good, or would that be helpful? All right, well, let's do it.